Hello friends, I am Dr. Punyadarshini Poonam Tripathi, Associate Professor in Agricultural and Food Engineering Department, IIT Kharagpur. So, in my last lecture, we have discussed about the advances in thermal processing of foods and their effect on the quality attributes. Although heat treatment drastically reduces the microbial load in the food products, but at the same time it also affects the sensory, flavor as well as aroma components of the food materials. As a result, the ultimate quality of the food is getting destructed, and in this context today we will be discussing the perpetuating the nutritional aspects of food with non-thermal technologies, because with regard to the improvement of food safety and quality, the non-thermal or emerging food technologies are being investigated and implemented to secure the food safety part. So, in this regard, the first module that we will be discussing today is non-thermal technologies and a brief review or overview and its status around the globe. And the second module will consist of some recent invents in non-thermal food processing. So, some of the references from books and journals are listed over here. Now, coming to the non-thermal technologies, as we know, the increasing global demand for minimally processed additive free food products with desirable sensory and nutritional value have attracted the attention of food researchers in innovative non-thermal or emerging food processing technologies. And these technologies are basically characterized by the impact of mechanical effects for disrupting the cellular membrane, and it increases the extraction of bioactive compounds by means of cell rupture. So, there are various types of emerging technologies are being explored, and out of which some of the important emerging technologies that are well recognized around the globe are listed over here. That is high pressure processing, pulsed electric field processing, ultraviolet light, microwave heating and power ultrasound. So, here we will be discussing about some of the emerging technologies in brief. So, coming to the advantages of non-thermal technologies over conventional ones. So, they are mostly preferred, the non-thermal technologies are mostly preferred over thermal technologies because they have shorter processing time, accelerated heat and mass transfer can be achieved, the product quality is much improved in non-thermal processed food materials, enhancement of the functionality, protection from environmental stress, enzyme deactivation is also one of the major important criteria of non-thermal processing, and ultimately that leads to extended shelf life of the food commodity. So, here we can see the potential for implementation of non-thermal technologies in various food sectors. As can be seen, a review has been carried out, and based on the review reports, average scores has been analyzed, and it was observed that high pressure processing is more popular and stands first in terms of non-thermal technologies, followed by UV, microwave heating and other non-thermal technologies, that is followed in a decreasing trend in the clockwise manner. So, coming to the high pressure processing, which is otherwise known as ultra high processing technology or Pascalization or high hydrostatic pressure processing also. So, HPP basically employs the application of high hydrostatic pressure, which is in the range of 100 to 1000 megapascal, and it is applied to the food product, and the food materials has to be placed in an enclosed vessel or chamber, and this process can be carried out with or without the supplementation of heat for a specific time period, which is sufficient enough to inactivate the harmful pathogenic and vegetative spoilage microorganisms and some selected enzymes. However, this high pressure processing is able to inactivate harmful pathogens and vegetative microorganisms, but the microbial spores are again highly resistant to high pressure conditions also. So, in this context, for example, Clostridium botulinum spores are highly resistant to temperature as well as to pressure also. So, to kill the spores of such microorganisms, we need to apply heat along with high pressure, so that the microbial spores can be effectively destroyed, and this type of process is known as pressure assisted thermal processing. HPP not only preserves the food from harmful microorganisms and undesirable enzymes, but it also offers protection to some functional compounds like antioxidants, probiotics, colostrum and lactoferrin. And it was also observed that the content of some of the functional compounds also increases with HPP treatment. Coming to the working principle of high pressure processing, it basically works on two major principles. One is Le Chatelier's principle and another is isostatic principle. According to Le Chatelier's principle, when a system at equilibrium is disturbed, the system responds in a way that tends to minimize the disturbances. For example, the phase transitions, chemical reactions and change in the molecular configuration that are accompanied by high pressure conditions, which is ultimately takes place due to decrease in the volume, is enhanced under high pressure conditions. As a result, the pressure shifts the system to that of the lowest volume. And in high pressure processing, the covalent bonds are not getting destroyed, whereas the tertiary or quaternary structure of the molecules are inactivated, or they are mostly altered at a pressure more than 200 megapascal. Similarly, next working principle of HPP is isostatic principle. Here the food is uniformly compressed and decompressed from all directions irrespective of its size and shape. The food materials has to be placed inside the pressure vessel and pressure has to be applied from all directions in an uniform manner, so that food shape is not getting distorted during the processing time. Now, coming to the mechanism of high pressure processing, the first mechanism is the generation of high pressure. So, as can be seen, the food materials are present inside the high pressure chamber. So, initially the food materials has to be packaged in sterilized containers and then they are loaded into the pressure chamber of the high pressure processing equipment, and then the desired pressure is applied for required time period. At the end, the pressure is released and the chamber is depressurized to remove out the packages. As can be seen, this is a high pressure processing system where inside the pressure vessel the food package is being placed and pressure has to be provided to the high pressure chamber. So, basically there are two important aspects how the high pressure is generated inside the high pressure processing chamber. So, as can be seen, there are basically two ways, one is direct compression, another is indirect compression. So, in direct compression, the compression fluid which is normally considered as water is loaded into the pressure chamber and then the pressure vessel is closed from the top and bottom. This is the top closure and this is the bottom closure through which the pressure chamber is properly sealed after the compression fluid is loaded into the pressure chamber. Then the pressure vessel is provided, as can be seen, a piston arrangement is provided with the pressure vessel. So, what is the function of this piston arrangement? When the fluid is pressurized by the piston, basically the fluid that we are providing into the pressure chamber, that is pressurized by the piston with the help of a low pressure pump, the working fluid or the compression fluid is pressurized by the help of the piston. Whereas, in case of indirect compression, the fluid is pressurized somewhere else, let us say it is in the pressure medium tank where the fluid is already pressurized and that pressurized fluid is fed into the pressure chamber with the help of an intensifier pump. So, these are two important mechanisms by which high pressure is being generated inside the high pressure processing system. And in direct compression it requires basically dynamic pressure seals between the piston and the vessel surface, whereas in indirect compression it requires static pressure seals. And there is also another way of heating the pressure medium, that is water combined with mineral or vegetable oil. Basically it is used for lubrication purpose with some anti-corrosive effect also. Now, coming to the pressure temperature variation during high pressure processing, as can be seen during high pressure treatment the temperature of the food material also increases with respect to the increase in the pressure. So, the pressure, temperature and time plot is being shown over here, and the variation of pressure and temperature along with the processing time is shown. So, it consists of three important phases. One is the pressurization phase, another is the holding period and then the depressurization phase. So, the pressurization phase or otherwise known as compression phase, followed by holding phase and decompression phase. In the pressurization phase, as can be seen, this is the initial temperature of the sample and P1 is the pressure at the initial conditions. So, during this compression phase there is an increase in pressure because we are continuously increasing the pressure from P1 to P2, pressure continuously increases and accordingly volume gradually decreases, which leads to an increase in the temperature of the food material. So, due to the increase in pressure from P1 to P2, it results in the rise in temperature of the food material from T1 to T2, and this results in the reduction of the volume inside the chamber. Next phase is our holding phase. So, the time period during holding phase is also known as the hold time or the dwell time. Very commonly it is known as dwell time, and during this phase, as can be seen, the product is held at a constant pressure, the pressure remains constant, whereas the temperature gradually drops down from T2 to T3. There is minor decrement in the temperature in the holding period. So, here the product is held at a constant pressure and temperature, but however, the product temperature and pressure are independent of the compression rate, but a slight decrease in temperature is also noticed from T2 to T3. And after that the decompression phase, because during the treatment time or holding time the most of the impact of high pressure is being affected, so that the product gets safe from microbial infestation, and after that in the decompression phase, which basically is denoted from T3 to T4, that means the temperature of the product gradually drops down because we are removing the pressure. So, accordingly pressure is at P4, from P3 to P4 the pressure gradually decreases as well as the temperature also decreases. Because as it is also seen that the temperature T4 is slightly lower than the initial temperature. T4 is the temperature of the food material, that means after the depressurization stage the final temperature of the product is slightly lower than the initial product temperature because of the heat losses during the pressurization period. Due to some heat losses that are taking place during the pressurization period, the temperature of the product at the final condition is slightly lower than the initial temperature of the product. Next, coming to the microorganism inactivation during the high pressure processing. So, what is the mechanism of the microorganism inactivation? So, most important part is due to the high pressure treatment, the shear forces that are generated are basically responsible for the disintegration of cell membrane of the microorganisms. As a result, they are getting inactivated or deactivated. Most vegetative cells are inactivated at pressures in the range of 300 to 600 megapascal, and it was also observed that gram negative bacteria are highly sensitive to pressure as compared to gram positive bacteria. And as already I have discussed that bacterial spores are very temperature as well as pressure resistant. So, we need a combination of high pressure and temperature to kill the bacterial spores. Fungi are less resistant than bacteria, and it was observed that at pressure below 400 megapascal, it is sufficient enough for inactivating most of the yeasts, and at pressures above 400 megapascal, that is in between 400 to 600 megapascal, certain modifications in the mitochondria and cytoplasm of the yeast cells are also observed, and molds get inactivated at pressures between 300 to 600 megapascal. Basically, the inactivation of microorganisms are achieved at different pressure ranges that is being provided here. Inactivation of enzymes during HPP, there is also inactivation of enzymes apart from destruction of microorganisms, as can be seen over here. So, due to the application of high pressure, the native structure of the enzymes, they are getting in a denatured form. So, the structural modification of the enzymes from native to denatured state is basically a biochemical reaction with equilibrium constant K, and the Gibbs free energy delta G can be related with activation volume, pressure and temperature and universal gas constant by Planck's equation, which can be provided over here. Delta G upon dP is nothing but equal to, this is the activation volume, which is related in terms of universal gas constant, temperature, d ln k upon dt. So, HPP does not affect the primary structure of the protein, tertiary structure is largely affected. Disruption of hydrophobic and electrostatic interactions during high pressure processing leads to certain changes in the quaternary structure also. Next, another important non-thermal technology is the pulsed electric field. So, pulsed electric field is described as a non-thermal food pasteurization technique, which utilizes the application of short duration pulses. This is very important. So, application of short duration pulses of moderate to high electrical field strength, that is in the range of 10 to 80 kilovolt per centimeter, that is given to the food products for destruction of microorganisms. So, in this process basically the food products are placed between two electrodes inside a chamber at mild to high temperatures in order to inactivate both spoilage and pathogenic vegetative microorganisms. The high voltage pulse induce irreversible structural changes in the cell membrane, leading to pore formation and destruction of the semi permeable barrier of the membrane. So, most studies have focused on PEF treatment effects on the microbial inactivation in milk, milk products, egg products, juice and other liquid foods. Coming to the working principle of the pulse electric field technology, the main important components of the PEF system includes a high voltage pulse generator, treatment chamber and some fluid handling systems along with control and monitoring devices. So, here inside the treatment chamber the food product is placed in a static or dynamic design. High voltage electrical pulses are applied to the electrodes. Inside this treatment chamber we have two electrodes in between which the food matrix has to be placed. So, the high voltage electrical pulses are applied to the electrodes. As a result, these electrical pulses are conducted into the food materials and the food product experiences a force per unit charge, that is responsible for the irreversible cell membrane breakdown in case of microorganisms. So, the applied high voltage results in electric field that causes microbial inactivation. Application of pulse electric fields of high intensity and duration it normally ranges from some microseconds to milliseconds, and that is sufficient enough for temporary or permanent permeabilization of the cell membrane. So, the effectiveness of the pulse electric field technology for microbial inactivation basically depends on the field strength, the treatment time and temperature, the pulse width, frequency and shape in terms of monopolar, bipolar, square or exponential shape. Then the electrode distance, which is basically known as the treatment gap. So, this is very important. The treatment gap between the two electrodes plays a huge role in defining the effectiveness of the pulse electric field implication on the destruction of microorganisms. Polarity and applied energy, these are some of the important parameters that decides the effectiveness of the PEF technology for the cell membrane permeabilization and leading to destruction of the cell membrane. Coming to the applications of PEF in food industries, mostly in food industries it is employed to treat some acidic fruit juices like strawberry, apple, orange and pear juices. Milk functional properties like coagulation, emulsification, capacity and foaming characteristics can be changed after PEF treatment due to the modification of protein network. There are certain advantages and limitations of the process also. Coming to the advantages of PEF technology, PEF is advantageous over the conventional thermal processes since it avoids the destruction of thermolabile compounds, which is very important aspect of the non-thermal processing, because in thermal processing the heat sensitive components of the food materials are getting destroyed at high or elevated temperatures, which can be retained with the help of non-thermal technologies. So, here we can retain the proteins, vitamins and enzymes, providing safe and self-stable food products with natural sensorial attributes, because the main consumers drive nowadays is towards safe and fresh like processed food. So, in that regard these non-thermal technologies can play a pivotal role. So, due to multiplicity of variables influencing the feasibility of PEF technology, this is one of the major disadvantages. There are various parameters that are going to affect the feasibility of implementation of PEF technology. For example, the product flow characteristics, electrode distance or that is otherwise known as treatment gap, then the viscosity of the product and conductivity. So, considering these parameters, it basically limits the application of PEF in commercial scale or industrial scale processing. This is one of the major disadvantages or limitations of the PEF technology. One of the very important non-thermal technology is ultrasound technology. So, basically as the name suggests, ultrasound, we can define sound as the continuous propagation of mechanic compression or wave that cause the particles to vibrate longitudinally and propagate throughout a medium. And according to the frequency range, sound can be categorized as infrasounds up to 20 Hz frequency, acoustic sounds up to 20 kilohertz, which can be audible to the human ear, and ultrasound above 20 kilohertz and up to 10 megahertz. So, based on the frequency range, the sound can be classified as infrasounds, acoustic sounds and ultrasounds. So, these ultrasounds again can be classified according to the intensity of the sonication at as given as low intensity sonication, that is energy level is less than 1 watt per centimeter square, which is used in several quality control processes and physical state of matter, and high intensity sonication where energy level ranges from 10 to 1000 watt per centimeter square, and this high intensity sonication is normally used for processing the food materials. So, low intensity ultrasound and high intensity ultrasound as we have classified them. So, low intensity ultrasound basically is non-destructive technique that provides information about the physico-chemical properties, composition, structure and physical state of the matter. And high intensity ultrasound, it is used basically for the disruption or destruction of cells, generate emulsion, promote chemical reactions, modify some crystallization process, and it also used for tenderizing the meat products also. So, the mode of action of ultrasound for destruction of microorganisms can be explained as the effect of inactivation of cells by ultrasound is attributed to again shear disruption, as we have seen in case of pulse electric field also. So, shear disruption followed by heating and free radical formation are the main mechanism for inactivation of microorganisms through ultrasound treatment. Ultrasound basically is propagated by a series of compression and rarefaction waves induced in the molecules of the medium through which it passes. So, when ultrasonic waves pass through a liquid, the major mechanical effects of ultrasound are provided when the power is sufficient enough to cause cavitation. So, cavitation along with the shearing forces are responsible for the destruction of microorganisms through ultrasound technology. So, due to cavitation, there is intense bubble formation which then hit each other inside the medium. So, in the medium very high localized temperatures are also generated, which is up to the level of 5500 degree centigrade, and high pressure also can be achieved, that is around 50 megapascal. So, with high temperature and high pressure conditions, the microorganism destruction is achieved. So, this high temperature and pressure causes extremely violent impulsions leading to thinning of the cells, followed by breakage of cell wall that releases the cytoplasmic content of the microorganisms, ultimately leading to their destruction or death. So, there are basically 3 different types of ultrasound systems are available. As we can see, the first one is a ultrasonic bath, second one is a batch type probe system, and third one is a continuous probe system for processing the liquid food materials. So, this ultrasonic bath is a very basic construction of the ultrasound systems, where ultrasonic generator is used to charge the ultrasonic transducers to generate the sound waves, and in case of bath type probe system, we have the ultrasonic transducers that provides the energy to the probe, which again agitates the liquid present inside the bath to affect the microorganism destruction. And similarly, in the industrial processing, we can see the continuous process here, where ultrasonic generator again at the top surface it is providing the required ultrasonication, and we have sample provided at one end and water can be released from the other end, and what samples present inside the ultrasonic bath are normally packaged properly, so that they cannot be removed out during the processing period. So, these are some of the emerging technologies or non-thermal technologies that are well established, but not yet fully commercialized due to certain limitations, because non-thermal technologies at their own cannot be sufficient enough for total destruction of microorganisms. So, in that regard there are certain research and studies needs to be investigated for further improvement of process design and technologies for successful implementation of these non-thermal processes throughout the industrial sector. So, coming to some advantages and disadvantages of the ultrasonication system. The advantages of ultrasonication system in food processing are the effectiveness during mixing of products, faster heat and mass transfer process takes place through this, because there is severe agitation takes place inside the ultrasound bath, reduced temperature increments during processing, selective component extraction can also be possible through ultrasonication. Equipment size is small, with small equipment size we can handle the process, and compared to other non-thermal processing technologies, this US or ultrasonication technology implementation costs very less. And some limitations of ultrasonication process is ultrasonication are highly dependent on sample matrix and the presence of a disperse phase, which may reduce the effectiveness of the method by wave attenuation. So, in this regard better optimization of process parameter is needed for its successful implementation. Thank you.